Welcome to Module 2, Subsurface Characterization. In Module 1, we explored how field development decisions are made. In this module, we focus on the information that drives those decisions. Before we can design wells, size facilities, or evaluate project economics, we need to understand the reservoir. This module examines how seismic data, well data, and reservoir engineering information are transformed into static and dynamic models that support the field development plan. By the end of the module, you'll understand how subsurface data becomes the forecasts and volume estimates that every later FDP decision depends on. The subsurface model answers three critical questions. First, how much hydrocarbon is present? Second, how will it flow? Third, how uncertain are those estimates? Every major development decision depends on these answers. Well count, well placement, facility size, production forecasts, and ultimately project economics are all derived from the subsurface understanding. Notice the direction of influence. The development concept does not determine the reservoir. The reservoir determines the development concept. Most of the subsurface work occurs during exploration, appraisal, and the early FEL stages. However, the model continues to evolve throughout the life of the field as new data becomes available. A useful way to think about the subsurface model is as the source of truth for the entire FDP. If that source of truth is wrong or overly optimistic, every downstream decision will be affected. Subsurface characterization relies on integrating multiple sources of data. The first is seismic data. Seismic surveys help us visualize the structure of the reservoir, identify faults, understand stratigraphy, and estimate fluid contacts across the field. The second source is well logs. These measurements are collected along the wellbore and provide continuous information about rock and fluid properties. The third source is core and cuttings. Unlike seismic and logs, these are physical rock samples. They provide direct measurements that help validate and calibrate interpretations. The fourth source is pressure and production data. Pressure measurements, well tests, and production history help us understand how the reservoir behaves dynamically. Each data source provides part of the picture. Seismic tells us where the reservoir is. Logs tell us what the rock may contain. Core tells us what the rock actually is. Pressure and production data tell us how the reservoir behaves. No single dataset is sufficient on its own. The purpose of subsurface modeling is to integrate all of these datasets into one consistent understanding of the reservoir. Before volumes can be estimated, we need to understand the geology of the reservoir. The first building block is structure. This describes the geometry of the reservoir, including traps, faults, and folds. Structural interpretation is primarily based on seismic data. The second building block is stratigraphy. Stratigraphy describes how rock layers are arranged and correlated between wells. It helps us understand the continuity of reservoir units across the field. The third building block is facies and depositional environment. Different depositional settings create different rock qualities. For example, a clean channel sand may provide excellent reservoir properties, while a shale-rich interval may provide very poor reservoir quality. An important point is that uncertainty in geology directly creates uncertainty in volumes. If we are uncertain about the position of a fault, the size of a trap, or the continuity of a reservoir interval, then we are also uncertain about the amount of hydrocarbon present. This is why appraisal wells are designed to answer specific geological questions rather than simply collecting more data. Petrophysics can be simplified into three key properties that appear throughout field development planning. The first is porosity, represented by phi, or phi. Porosity measures how much space exists within the rock to store fluids. A rock with higher porosity can generally hold more hydrocarbons. The second is permeability, represented by K. Permeability measures how easily fluids can move through the rock. Two reservoirs may contain similar volumes of hydrocarbons, but the reservoir with higher permeability will generally produce more easily. The third is water saturation, represented by SW. Water saturation measures how much of the pore space is occupied by water rather than hydrocarbons. Higher water saturation generally means less hydrocarbon-filled pore volume. These three properties are fundamental because they feed directly into volumetric calculations and static model construction. In very simple terms, porosity influences storage. Permeability influences flow. Water saturation influences hydrocarbon volume. This is one of the most important distinctions in the entire course. The static model describes what the reservoir looks like. The dynamic model describes how the reservoir behaves. The static model is a three-dimensional representation of reservoir properties. It contains structure, facies, porosity, permeability, and saturation distributions. It represents the reservoir at a single point in time and is used to estimate volumes in place. The dynamic model builds upon the static model. It simulates fluid flow and shows how pressure, production rates, and recovery evolve throughout field life. A useful analogy is this. The static model is a photograph. The dynamic model is a movie. One shows the reservoir's current state. The other shows how the reservoir changes through time. Everything related to production forecasting in later modules ultimately comes from the dynamic model. This slide summarizes the overall workflow used to move from raw data to production forecasts. The process begins with interpretation. Seismic and well data are interpreted to define structure and stratigraphy. Next, a static model is constructed. The reservoir grid is populated with rock and fluid properties. From this static model, in-place hydrocarbon volumes are estimated. The model is then converted into a dynamic simulation model capable of representing fluid flow through time. The dynamic model is calibrated through history matching using available pressure and production data. Finally, the calibrated model is used to generate production forecasts. Notice that each step builds on the previous one. Errors introduced early in the workflow can propagate through everything that follows. That is why quality control at each stage is critically important. Once production data becomes available, the dynamic model must be calibrated against reality. This process is known as history matching. During history matching, uncertain parameters such as permeability distribution, aquifer strength, or fault transmissibility are adjusted until the simulated results align reasonably well with observed field performance. It is important to understand what history matching does and does not achieve. A history-matched model is not proven correct. It is simply a model that is consistent with the available data. In fact, multiple different models may reproduce the same historical observations. This is known as non-uniqueness and is a fundamental characteristic of reservoir simulation. The further a forecast extends beyond the period of observed history, the greater the uncertainty becomes. Therefore, history matching should increase confidence in forecasts, but it should never create a false sense of certainty. The concept of uncertainty introduced in Module 1 becomes much more concrete here. Because subsurface data is limited, multiple geological and simulation models can often satisfy the available data. Rather than selecting a single best model, industry practice is to generate multiple realizations and evaluate the full range of possible outcomes. These results are commonly expressed using the P90, P50, and P10 convention. P90 represents a conservative outcome. P50 represents the median or best estimate. P10 represents an optimistic outcome. Importantly, this approach applies not only to volumes but also to production forecasts and economics. The goal is not to eliminate uncertainty. The goal is to quantify it and communicate it clearly. One of the most common mistakes in field development planning is focusing exclusively on a single best case number while ignoring the uncertainty range that surrounds it. The industry requires a common language for discussing hydrocarbon volumes. That language is provided by the SPE Petroleum Resources Management System, or SPE-PRMS. The first category is reserves. These are discovered volumes that are commercially recoverable and approved for development. Reserves are commonly classified as 1P, 2P, and 3P. The second category is contingent resources. These are discovered volumes that are not yet considered commercially recoverable or have not yet reached development approval. This is often where a field sits during much of the FDP process. The third category is prospective resources. These are estimated volumes associated with undiscovered accumulations and future exploration opportunities. The important distinction is that reserves have both technical confidence and a pathway to commercial development, while resources still require additional work before they can move into the reserves category. The science may be the same, but the data acquisition strategy is very different between onshore and offshore developments. In onshore settings, wells are generally less expensive. Operators may drill hundreds or even thousands of wells across a development area. As a result, uncertainty can often be managed statistically using large datasets and type curves. New wells can rapidly update the subsurface understanding. Offshore developments operate under different constraints. Appraisal wells are extremely expensive. and only a small number may be drilled before major development decisions are required. As a result, offshore projects place greater emphasis on acquiring high-quality seismic data and carefully designing each appraisal well to answer specific questions. This difference explains why unconventional onshore developments often rely heavily on statistics, while offshore projects place greater emphasis on extracting maximum information from a limited number of data points. This slide brings together several concepts we've discussed throughout the module. The reservoir trap cross-section illustrates the geological framework that controls hydrocarbon accumulation. The P90, P50, and P10 chart illustrates how uncertainty is represented as a range of possible outcomes rather than a single estimate. The seismic structure map demonstrates how subsurface geometry is interpreted and mapped before models are constructed. Together, these images summarize the progression from geological interpretation to uncertainty assessment to reservoir modeling. This case study demonstrates how subsurface characterization changes when data becomes abundant. In the Permian Basin, operators often have access to thousands of wells. Because of this dense data coverage, characterization becomes increasingly statistical. Rather than building highly detailed reservoir simulations for every individual well, operators frequently use type curves derived from large populations of offset wells. The low cost of drilling creates another important advantage. Early wells can serve both as producers and as sources of information. New data is continuously incorporated into forecasts, creating a rapid learning cycle. The key lesson is that abundant data allows uncertainty to be reduced through volume and repetition. This example illustrates the opposite situation. In deepwater developments, appraisal programs may consist of only 1 to 3 wells before concept selection begins. Each well is expensive, making data acquisition highly selective. As a result, every appraisal well must be designed to answer the most important uncertainties affecting development decisions. Additional information often comes from advanced seismic technologies such as 4D seismic monitoring. In this environment, it becomes especially important to communicate uncertainty honestly. With only a small number of data points available, the objective is not to identify a single correct model. The objective is to understand the full range of plausible outcomes and make decisions accordingly. This slide connects everything in Module 2 directly back to field development planning. Volume estimates and recovery factors define the size of the opportunity and establish the potential economic value of the project. Reservoir connectivity and heterogeneity influence how many wells are required and where those wells should be placed. Production forecasts generated by the dynamic model determine facility capacity requirements and export system sizing. Pressure forecasts and aquifer behavior influence whether pressure support systems such as water injection or gas injection will be required. Notice that nearly every major FDP decision can be traced back to a subsurface model output. This is why subsurface characterization is not an isolated technical activity. It directly drives development strategy, project scope, facilities design, and economics. Module 3 begins exactly at this point, where subsurface forecasts are translated into a wells and production plan. The main points from this module are straightforward. The static model describes the reservoir at a point in time. The dynamic model simulates reservoir behavior through time. History matching calibrates models against observed data, but it does not eliminate uncertainty. P90, P50, and P10 ranges are essential because multiple subsurface models can often explain the same data. SPE-PRMS provides the industry's common framework for reserves and resources classification. Finally, onshore and offshore developments rely on the same scientific principles but use very different data acquisition strategies because of their fundamentally different cost structures. In Module 2, we developed an understanding of the reservoir and generated production forecasts. The next question is straightforward. How do we convert those forecasts into a practical development plan? Module 3 focuses on wells and production forecasting. We will examine well count, well placement, development sequencing, production profiles, and how dynamic model results are translated into a field development strategy.